point. That's all. Okay. So okay, let's get to work. And apologize for one thing. Well, personally, I don't like to work in the evening. Okay, you boys can get out and come back around 7:45. Okay, and about take a 5 minutes break, and then we'll close. We will close at 9. All right. Okay. So this is what we talked about yesterday, right? How to design a simple gate based on the a few steps that I introduced. So let me refresh your memory again. So if you are given an equation, Boolean equation, then what you do first, okay? You are given an equation, what you do? This is the equation. For example, yesterday I used an AND gate, right? Today I'm going to give you another example how to use the OR gate. So this is what we taught yesterday. So basically, you group all the PMOS devices on the top, where they are coupled to the power supply VDD, and all the N transistors are grouped together in the bottom, and coupled to the ground or 0. And in the middle is where the output is. That's a basic idea. This is a very fundamental one. If you get to know this, then at least you know one of the most efficient approach to design a gate using transistors. And besides, we also talk about how to tune the size properly. So basically, we have several rules, okay? Simple rules. For example, we know inverter that we'd like to have 1 versus 2. Okay, let's assume the size, I'm talking about the width. The width of the P transistor must be twice as large as that of MOS transistor, because the mobility of a holes is only half or maybe 1/3 of the electrons. That is why. So basically, we assume the length is the same. We like to have 2:1 width ratio, so that the current in the P device and the N device will be equalized, and the charging discharging time will be almost the same. That's a basic the sizing info that we need. And then we talk about one thing. Okay, if you're given a Boolean equation, step number 1 is to reverse it. Reverse it. Okay, I'm giving you this example. Let's try this one. Okay, if this is the equation that you are given. Okay, for example, this is a NOR gate. Okay, the step number 1 is that, okay, we reverse it. We use a G, which is the inverse of excuse me, of F. Then we have A plus B. And then we see that there are plus. Plus stands for what? Stands for parallel. Okay, so we understand that, okay, in the bottom of our design, to realize this gate is that, okay, we are going to have two N transistors. They are both, okay, they are floor plan as a pair of parallel stuff. So this is A and this is B inputs. So basically, we understand what the hell is this. This is for the bottom. Then based on that observation, we know that we are going to have output over here. And of course, we have a load. This is a basic idea. Then step number 2, okay, after we derive the M block, then we are going to use a duality. Dual. Dual means that, okay, dual means N and P block versus P block. Okay, if they are parallel, if transistors are parallel, then the other will be serial. And it works the other way around. So if we see we have two transistors controlled by A and B, they are in parallel in the M block, then we are going to have a dual. That is, we are going to have two transistors, P transistor, they are serialized. Okay, serialized. So this is a serial. Okay, this is parallel. We call it dual. And they are controlled by the same group of signal. Okay, then we show them together. we use is short them together. All right, and this one goes this way, short them together. Okay, how do we prove that it works that well? Okay, this is for the dual. Okay, this is for the dual. Then we check. Okay, check. Okay, if the function is good. Okay, how do we do that? It's pretty easy. We use the table over here to make sure that we are doing the right thing. And there are a total of 4 combinations for 2 input signals, which are 0, 0, 0, 1, 1, 0, and 1, 1, right? So let's find out whether the output is this way. Okay, then we check. How to check? If, as we said yesterday, when we have an N transistor, it is used to pass low signal good, okay, because it is good for discharging. So when these, both of these are off, are 0. When both are 0, that means this one is on, this one is on, and here both of them are cut off. So there will be no, there will be no discharging pass. The only thing we can see from this diagram is that we are going to have a current, okay, flowing from the power supply to the load, So sooner or later, okay, the voltage here will be charged, okay, as high as the power supply. So that is equal to 1. 0, 0, we are going to get 1. Okay, 0 get a 1. And then what's going to happen? What's going to happen is that if one of them is on, that means one of them, it's this one or this one. It doesn't matter. So one is on, the other one is off. That's fine. So for example, A is right now is 0, is 1, sorry. This one is 1, is 1. So one will be turned on, and this one will be off. Even though that B is on, it doesn't matter anyway. So there will be no pass to charge the load. However, by contrast, we are going to find out there is a pass, okay, to discharge the voltage or the charge on the capacitor to ground. So in this way, we find out either one of them is 1, we are going to have 0. Okay, we have 0. We have 0. Of course, if both the transistors are on, almost are on, we are going to have 2 pass to ground this output voltage to get 0. So apparently, according to the definition of NOR gate, this one is good. This definitely is a NOR gate, right? So we prove that this is good. In terms of functionality, this one definitely will work, okay? But we're not talking about the performance, we're talking about the functionality. So that's one thing. So we prove number 1, this is good. And then we got to change the size. The assumption of the size as the length is the same. We only tune the width because students like to have a lot of information about the size, so they don't have to waste their energy to find out the correct size or the optimal size for the operation. So let's check this out. So I'm going to erase everything here. Now of course, right now we already make sure that this one works just fine. So let's draw the inverter over here to make a comparison. So this is the inverter, okay, a regular inverter, which has double size of the V's for the P devices and a single size of W, right? That is apparently the the size required to have a balanced, rising and falling edges. Right now, okay, let's compare these 2 parts. Okay, we like to have the same performance for the NOR gate that we just created. Okay, we like to balance, equivalent, equalize the rise time and the fall time of this new OR gate. So how are we supposed to do? It's pretty easy. So if you see they are in serial, okay, then you increase the size, increase width. If you see parallel, you don't do anything. Nothing happened. Nothing happened. Because if we turn on this one with one single input, then one of the input that we use to turn on one of the transistors, the effect is the same. So if we see parallel, you don't have to do anything. So I guarantee you that the size for these two transistors will be the same as the one in the pull down block of inverter. So it's guaranteed to be W. However, if you see serial, then you're in big trouble. Because we like to have the same rising time and falling time. But if we stack or serialize these two transistors, as I said yesterday, if you consider this is equal to an R resistor, then you are going to have R and R. You're going to have 2R. Okay, because they're in serial. So the impedance in this path will be larger than the original one. So we don't like that. We like to balance it because the pull down is the same as the right-hand side. So what we do, we like to do this way. We like to cut in half. Then we're going to have the single R, just like the one we had before. All right? So how do we reduce the impedance? According to the Ohm's law, all we need to do is that increase the size. When the size of the transistor increases by double, then the resistor, the impedance goes down half. So basically, what you should do is you are going to increase the size. Okay, because we double it, equal to the 4 times of the original width. Then you are going to have almost a perfect design for this NOR gate, because after our roughly calculation, all you have to do is we increase the size width, width of the PMOS devices on the top. Then you are going to have about the same charging time, just like we had for the inverter. Is that clear? Really easy, right? Okay, even undergraduate students, even the elementary school kids can follow the same rule. And this kind of implementation, as I said yesterday, is called a FFF plan implementation. All right, got it? No problem, right? So it's pretty easy, very systematic way to do the design for the simple gates. Now let's check a little bit more complicated gates. Well, this TS should do their job better. Okay, remember this gate? This is a gate that we show in yesterday's course. See that? We have 2 transistors in serial in the bottom. So apparently this is a NAND gate. NAND gate, right? Remember what I showed you in the classroom yesterday? This is the AND gate. So this is the counterpart of the NOR gate. So apparently, and we also show you that, okay, the size of the pull down here will be double because they're in serial, right? Okay, so you got a 2W, 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 2W over here. So this is a design of 2 input NAND gates. Now we call this a simple gate because they are basics. Now let's check the other one. Okay, what is this? Okay, there is no equation, but this example is quite easy. So I will never make your life miserable, all right? So let's check what this equation is. Suppose you are given a circuit like the one on the screen. What is that? Okay, you check. Because the left-hand side is a switch, it's a switch-based design. The right-hand side is a mouse-based. So basically they are the same. All right, basically they are the same. Okay, no difference. So you check all the equation over here. You see that? In the bottom here, you see that the W and X. Okay, those transistors they control are in serial. Got it? They are in the stack up. And similarly, we have two transistors controlled by Y and Z inputs. They are in serial. So we know that in the bottom that we have W and X, and the other one is Y and Z. Is that clear? Right? And now let's check this one over here. See that? And this pass, let's assume they are the single device. This pass and this pass, they are in parallel. Right? They are in parallel. So we are going to have this one. So we are going to have the equation over here. All right? Okay, that's one thing. Then let's check another way. And this is because this one goes to the bottom. So apparently, this is the G, which is the inverse of a certain equation. A certain equation. Then we can move this one to over here. And take this away. So if we just look at the bottom of that circuit, we understand we have an N, then we have an OR, then we have an inverse. Okay, so this equation is abbreviated as AOI. AOI. So this is AOI function. Just over here. Just over here, AOI. So when you see the term AOI, that means, okay, the AND, OR, and inverter, they are combined together. A little bit more complicated. But it's still very simple. Okay? And the next thing we have to check, okay, make sure that this one works as we expect. So how do we make sure? See, we remember the theory that I used to draw the symbol gate. We have a dual to follow. So we have to follow. We have to check that. Okay, W and X, they are in series here. On the top, you see, those PMOS transistors that they control, they are in parallel. So this is good. So the duality of W and X stands still. Then we check the Y and the Z. They control two transistors here are in serial. So those two that they control on the top of music are parallel. So it is also good. So the duality stands still. The last thing we have to check, make sure that everything just fine. See, these pass, these two, and these two, they are in parallel. So for this group on the top, the duality over here, and this group on the top over here, they are in serial. So the group, look at it from the group way, they are also dual. So we guarantee this function is perfect. It's a rationalized design. Okay, is that clear? Understood? Okay, no problem at all, right? So then the next thing you want to ask is how to tune the size. It's almost the same. It's almost the same. Okay, in the bottom you see that we have two transistors. Okay, they are stacked together. So the original is W. Here you got to have 2W over here. 2W. Because they are parallel, we don't care. Parallel is good. They are not going to cause any trouble. And for the counterpart on the top, we are going to have two groups of P devices over here. P devices is here. So the original P devices is 2W. When they are in parallel, it's the same. Sorry, this is wrong. But you consider that they have two groups stacked on each other. So apparently we have increased the size to 4W for everybody on the top. So this is how we tune the size correctly. So I always tell my students, okay, my graduate students, okay, don't just sit in front of your computer and use a brutal force trying to find out the best answer to fit what the professor asked. Okay, you got to have some fundamental strategy to find out at least some optimal size information you need, so that you can quickly get your final answer. Okay, this is one of the efficient ways to find out the size information. All right, don't just sit in the front and try different sizes and keep trying and trying. Okay, that does not make sense. You are wasting your life and abuse the computer power. Okay, is that good? All right, okay, let's move on. So right now we have a basic understanding of switch logic circuits. And in fact, we can stop right here to close lecture 2, because all you need is to understand one of the ways to design a simple gate. However, there are many other ways in textbook or in many literatures. I would like to spend some time with you to understand how other people come up with different design. The one I just showed you is very classic. It's very legacy approach to do the design. So now let's go to others to see what other systematic designs have been published in papers and textbooks. Okay, so first thing first. The left-hand side is the AND gate, and the right-hand side here is a simple way to implement it, but the answer is this one is bad. This one is bad. Why is bad? Is anyone to tell me why it is bad? This is the AND gate, right? And based on the switch logic, so we just combine two transistors. They are driven by two individual inputs, and one side is coupled to VDD. So it's supposed to work like an AND gate, right? When X and Y equal to high, VDD will be passed to F, instantly. Okay, very straightforward. But however, I'm telling you, this is totally wrong. Okay, don't think this is correct. Can I erase this? All right. So I think everybody understand all the steps to to design a simple gate. So why this one on the screen is bad? Okay, when we're talking about the AND, you will come to your mind to draw this truth table. Okay, you got 0, 0, 0, 1, and this is what? This is the F, A and B. Okay, the left-hand side is a gate, and this is a required function for the function table for the AND function. Okay, but that circuit's over there. I'm going to tell you how bad that is. Okay, it is a poor circuit. Okay, this is VDD, right? This is VDD, right? Okay, then logically it is equal to 1. Now, right now we have A and B to drive it, and we are supposed to get an F on the other side. Okay, let's check from the bottom one, because intrinsically we think, oh, this one works just fine. So when this is high, this is high. So we are going to turn on this, turn on that, right? According to the transistor, very basic MOS transistor. So we're going to turn on that. So you are going to assume this signal will be automatically and faithfully passed to F. But reality is, okay, even though you are given too high signal to drive these two transistors, you are not going to get the exactly high voltage. Because as we said before, this point here, if it is VDD, then this is VDD. Everybody's VDD for this device, it will not turn on. It's dead. So you're going to get at most this much. That's all. Right? Then you're going to pass this voltage over here, and this is VDD. Then at least you gotta have a voltage drop of VTH. So at most, the highest voltage you can get is VDD minus VTH. That's what you can get. That's it. Nothing else. So even though I use very high voltage over here, you are going to get a weak one. A weak one signal here. Okay, that's the first thing. The second thing is even worse. Logically speaking, this thing it's not right. Oh, check this out. Okay, check this out. Now, let's assume the initial condition. You have a 1 and a 1. Right? You have a 1 and 1. Now, VDD is present here, and you accept that I'm going to get VDD minus VTH, this voltage. In the next time period, next time point, okay, in the next sampling point, this one, B over here, change to 0. What happened? According to this table, when B is switched to 0, I'm supposed to get this one, right? Then what did you get over there? What did you get over there? When this is 0 and this is still 1, the current still go over here. However, here, this one is cut. It's cut off. Okay, it's cut off. That means nothing will go through this transistor theoretically. And what happened before, this is a voltage, stand there. There is no pass to ground. See, you have a parasitic capacitor over here. So we have something here. Since this one is cut off, how the hell the voltage and the charge here will be discharged to ground? It's impossible, right? So this guy will stand there for a while. Okay, it will go down smoothly and gently, but definitely it will not be ground. So according to the definition of this truth table, this thing cannot work as a real AND gate because the functionality is totally wrong. Is that clear? Okay, so you can switch the input over here. This is 0 and 1, and this one is cut. It's the same. You still don't have the ground pass. Since you don't have the ground pass, how the hell you can ground it? How the hell you can change the output to be 0? It's impossible. All right, so remember that this is biggest problem of the latest logic, not just the voltage level dropping. The functionality is totally wrong. All right, and this is another logic over here. Can this logic correctly implement this function? See, we have a XY, we have a YZ, we have a Y, sorry, this is wrong, this is XZ, sorry, my bad. So XY, YZ, and XZ, my bad. All right, never mind. So here you see that we have this one. It's controlled by Y and X. That's for the first term. And then we have Y and Z. That's for the second term. And the last one is X and Z. That's for the third term. I'm sorry, this is bad. All right? So, and then we hook them together as a wire, as an OR function. But if the above is wrong, how the hell this one can be correct? It's impossible. It's impossible. See? This term is wrong. It does not hold because this function cannot be realized, but that kind of logic is impossible. So how the hell this one can be correct? No, it cannot. All right, it cannot. So just forget about it. So the switch logic circuit, ideally, it can be used to realize any given Boolean function. But the thing is, we cannot directly implement it, just follow the equation over there. We got to do something else to make sure that this thing works just fine. So the same thing happened here, see? What if x becomes 0? Becomes 0, and whatever happened will stay there. Whatever happened will be stay there. Then you still don't have any ground path. You cannot discharge the output. Okay, no way that it goes to ground. That's it. Okay, end of the story. All right, now let's go to how do we fix that? So the basic rule here, please remember that. Okay, this is very important. When you do the design, okay, rule number 1, okay, for the beginners, the function or a signal summing point, where is that? Where is that? This is a summing point. Okay, you have multiple paths coming over here. This is a summing point. Okay, must be always be connected to 0 or 1 at any time. You cannot connect it to both. Okay, you can make sure that it is connected to at the period 1 connected to 0, period number 2 connected to 1, but you cannot connect the same point to 0 and 1 simultaneously. That's a rule number 1. Don't do that. Otherwise, you have a problem. Okay? And rule number 2 is called a node conflict-free rule. The functional signal summing point must never be connected 0 and 1 at the same time. See? You can only select one of them. Okay? You cannot have both. Otherwise, it will become ratio design. So if you violate this rule, because this is good, so this kind of design is a ratio-less design. Okay, if you violate these 2 rules, I'll give you an example. What is that? Okay, if you follow this rule, basically, all the example I already show you follow this rule. They are considered as a ratio-less design. So if a circuit or a design using a transistor, you don't follow this rule, then you're in trouble. I'll give you an example why. Okay. Okay, let's assume you have this kind of a scenario. You have 2 transistors. They are both N transistors. They are both N. Okay? They are both N. So it's equivalent when they both are on. Let's say A equal to 1, B equal to 1. What's going to get here? What's going to get here? See, this is 1, so this is turned on, right? And this is 1, this is turned on, right? So everybody's turned on. So what is the voltage here? You cannot decide, you cannot determine. I'll give you another more detailed analysis. So when this is 1 on, so we have a current coming from the top. And since there is no path, so the current will go down to the ground as well. So we have the same I on for everybody. I on for everybody. Right now, what is a ratio design? If you can consider when this is on, it is equal to the RB. We have a small resistor over there, equivalent resistor. Then we have a RA. We have RA over there, right? So the voltage here, V out, it will become I on times RA plus RB over RB. Is that correct? Is that correct? Very simple circuit theory, right? So the VR will go this way. How to decide the RA and RB? It depends on the size. WA over LA, WB over LB. Let's assume that the lengths of both transistors are the same. So what you're going to get is this way. Right? Is that correct? Okay. So the RA, what is the relationship between the WA and RA? They are inverse. They are inverse. They are inverse, right? So you plug in this information into that, you are going to get this one. 1 over Now we have a very funny story. What is that funny story? Look at these numbers here. So the output voltage could be very high. Could be very high. How do we do that? If RB is much, much larger than RA, then this one can be ignored. So these were very, very close to VDD. Right? You know what I'm saying, right? And then, on the contrary, it was very close to the ground. What? If RB is very, very smaller than RA, when RA is big, and this term can be ignored. So we have something very small. So the funny thing is that the size ratio will determine whether the output is close to 1 or close to 0. So this kind of design is called ratio design. That's bad. It's called a ratio design. Why? Because the output voltage depends on the ratio of the pull up and the pull down. This is only one example. And why is bad? Because you run into a situation, a signal summing point, okay, connected to 0 and 1 at the same time. If you run into this kind of a problem, I guarantee you're going to have a ratio design over there. And then you got to select the size even more carefully. Otherwise, you will generate a wrong output, a wrong logic. Is that clear? Very simple and straightforward. So a lot of students ask me why sometimes the circuit doesn't work. I ask him one thing. Do you make sure that your design is a ratio design or ratio-less design? And this is a ratio design. All right? Are we good? All right. So I wasted too much time on these two rules because I think this is quite important. All right. So let's elaborate those rules. Okay. So these are the basic rules. Ensure the correct logic function. Make sure the function is correct. Okay. Rule number 2. You got to distinguish ratio-less design or ratio design. You see my point? That's why I have to spend some time to explain what is ratio design, what is not. Okay, so those circuits that I demonstrated yesterday and earlier in this lecture are ratio-less. But if you find out there is a point, summing point or any point, okay, the output, okay, coupled to the VDD in the ground simultaneously, then you guarantee to have this one. Okay, so ratio-less logic is good for the beginners. Okay, after a while, you'll become very familiar with the design. Maybe you will like to use a ratio design because ratio design, in certain cases, they are good. They are good. Okay, but not yet. We're going to talk about later. Okay, what is the ratio-less design? Okay, I explained to you what the ratio is, what is not the ratio. Okay, so that's about everything. Then we'll go to some fun parts of new design approaches. Okay, the rule number 1 is a channel's expansion. So it's quite easy. Don't be scared. Don't be traumatized by the equation on the top. It's really easy. So on the top is a general formation, general form. Okay, if you are given a Boolean equation with n variables, okay, you can decompose to any variables, okay, by this way, okay? So how to decompose it? We select I, the ith variable, anyone, and the other one, okay, the original equation, and that one, the variable is replaced with 1, plus the inverse of this variable to time the original equation where the original xi is replaced with 0. That's it. So this is, excuse me, this is the equation, and this is a graphic explanation. So you are given an equation with 4 variables. You can decompose it from the top to the bottom, one by one. Okay, so you're gonna next question we ask is, why do you have to do that? As I said, you don't have to do that. I'm just showing you different design approaches. Okay, the one I show you before this slide is good enough to realize anything, any equation. Okay, but there are other guys. They have their efficient approaches to realize a given Boolean equation. So let's go to the example over here. So the original equation can be decomposed as this one plus this one. Okay, so we take the W out and plug in the original W with 1. We get this partial equation, and the other one is that we plug in the 0 times the inverse of W. Then we get the exactly same equation as before. Then you can do it recursively all the way down to the bottom. Okay, and this equation is developed by some guy called Shannon. And Shannon is a genius. Shannon is a genius. Okay. Have you seen the movie called Tenet? Tenet. 中文叫做天能 Tenet. Okay, Tenet has a very important assumption. That is, the time goes with the flow of entropy. Entropy stands for randomness. Okay, or stands for randomness. So, entropy, who come up with the first concept of this entropy? That's Shannon. Shannon. All right, this is a guy. Okay, this guy, okay, when he was hired by AT&T, in his first 3 years of career, he did nothing. He did nothing. He just hanging around in the AT&T Bell Lab and playing checker. And someday, somehow, he just woke up and come up with a lot of wild thinking, blah, 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 and then he defined the entropy. Entropy is used to describe the randomness. Okay. And randomness is the arrowhead of time. Okay, entropy. Okay, this is a word. It is equal to the P log P. Okay, P is a probability. Okay, entropy. Well, it's not covered in this course. Okay, it's just a story to tell you how smart God is. What is entropy? I'll give you some example. Okay, right now, if we go to a train, okay, everybody took a train before, right? If you never take a train, please raise your hand. Okay, see, everybody is now. At the starting station, every passenger is walking to the coach, okay, the cart, and they put their luggage on the shelf, on the top. Okay, then everybody line up so good. It's in a straight line. That's fine. Then after a while, after the conductor blows a wheel and the train starts to travel. Okay, what happened to those luggages on the shelf? They will bump up and down, right? So it'll be randomized. Have you ever seen another occasion? All the passengers, okay, randomly place their luggage, and as the train travel a while, everything back to the shelf. Have you ever seen that? Never. Okay, So the only possibility for things naturally, the things is to be randomized following time. If you can reverse the randomness, that means you can reverse the time. That's the basic assumption of Tenet. All right, so it's kind of amazing idea. All right, so we gotta give the credit to the director, Chris Nolan. I'm his fan. Anyway, well, we're not going to talk about that. Okay, we're going to talk about this one. So if you're given an equation like this one, okay, how do we decompose it? And we have not talked about why we need to decompose it, but let's show you how to decompose it. See that? This is original equation. Then the step number one, we pick up the one that we don't like. Okay, let's say x. So what we do? Okay, we substitute the x with 0. So we're going to get the 0 here, and yz is the only term left here, right? 0, 0 here, and this is the only term left. So we are going to get x bar times yz for the first one. Okay, and how about the next one? So we're going to substitute the x with 1, okay, over here. So we're going to get a y plus z plus yz. Okay, that's the first level decompose. So what we get? We get this one. See that? We get this one. See that? Okay, now let's check whether this thing is equivalent to the original one. Okay, that's something we'd like to prove. Okay, then you use a very basic algebraic manipulation. So we remove the bracket away. This is a term left over here. This is xy stands here, xz stands here, xyz comes over here. Is that correct? Right? Everything's good? So check these two terms. We have x bar, we have x. They have a common factor yz. So these two terms can be combined together and erase the x. So what's going to get is that we are going to have yz for these two terms, xy and xz, which are exactly the same as before. See? So after the decomposition, now we get the same thing. So that proof, okay, we had a mathematical proof. We lack the example proof. So this proof that the Shannon expansion works just fine. All right? Is that cool? Okay. So if you can come up with some equation like that, you can name that equation after your name. Okay, then it will exist, it will stay in the textbook for the rest of a human being. All right, that's the way how to do it. The Shannon's expansion theorem. All right, why do we need that? Because somebody used it to come up with a crazier idea. Okay, right now let's assume we have two sets, big X and big Y. And this is M variable, this is M variable. All right, okay. And we have to define one term, which is called the residue. Residue is something left that remains, just like garbage. Garbage is not the right term, because something we left behind, residue, is residue. So residue of f over x with respect to y is denoted as f sub y big X over here. And I don't want to tease you with all the mathematical symbols. Don't panic, okay? You will not figure it out. All right, so we set all complementary literals equal to 0, and we set all true literals equal to 1. That's how we do it, all right? So let's check. The best way to describe a series is to use examples. So this is how it works. Okay, above the top one is a very long, lengthy, equations. We hate that. So we can use a residue theory. Okay, how do we do that? See, this is the way to do it. We take W bar, X bar, Y bar over here. Okay, and then we plug in zeros. Okay, and this stays there. Then we got nothing, 0. Instead, we plug in 1, 0, 0, I can do the same thing to the top and keep Z over there because 0. You might be wondering why we have to do this. Okay, be patient. So how many combinations we have for W, X, and Y? A total of 8. Is that right? 0, 0, 0, all the way down to 1, 1, 1. And we are going to get different output over there. So we are going to go through that. Okay, we skip all this to get this, I'm sorry? Okay, so then we follow the same way. A total of 8 residues. They are respective to what you want to do. What you want to do. For example, the last one, we plug in 1, 1, 1 to get the residue over there, Z. Okay, this is one going over there. So this is a switching example. And this kind of thing is very good for implementation efficiently for switching logic. All right? So besides the equation, we prefer to see figures or tables. So we use the tables to show that. And that will be a little bit more convenient for students to learn. So right now, let's use a map similar to the K-map you learned when you were a freshman. So we have 2 to the m's columns and 2 to the n minus m rows. So we can, arbitrarily select how many variables we want to do the residue operation. Okay, and the residue will stand here, will be here. Okay, so this is the number we plug in, just like the one we had before. All right, and this is the equation way, and this is the map way. So let's try this one to see what happens. All right, now you're going to love this one. So what is the above? This is the, if you still remember, it is called the canonical form representation for a Boolean equation. Okay, I don't care, we don't care what kind of variable you use. All we need is some numbers. So we have 0, 1, 3, 5, 6, 10, and 14 as a high. Okay, it's called the min terms. Okay, the min terms. All right, so what we got? Okay, it looks like a K-map, but it's not. The K-map, let me refresh your memory. The K-map that you learned when you were a kid, when you were undergraduate, WX, Y, and Z. This is the K-map, right? That you learned before. 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and then you are taught to plug in all the numbers over there. 0, okay, sorry. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Then your professor certainly will tell you, you just plug in 1 over here, then we got a 1, and this is 0, and then 1, and number 3, number 5, number 6, then 10, and 14. Then your professor told you how to group these ones, then find out the minima set. Is that right? That's what you learned when you were young, right? Okay, about 2 or 3 years ago. This is K-map. Now we are not talking about K-map, we talk about the residue map. Okay, it's different. So this is a residue map because we decompose. We like to decompose the original equation into this way. We pick one of the 4 variables, and then we decompose the rest because we have 3 variables left, from 0, 0 to 1, 1, 1. Okay, then 0, 0, 0, this is number 0. 0, 0, 0 is 1. So we have 0, 1, 2, 3, 4, 5, 6, 7. So the order of the residue map is a natural order. It is not the same as a K-map. Because a K-map is not a natural order. See that? We flip this too. Because we wanted to do the merge and the grouping. That's why. But here we don't do that. We don't care. So we just follow the natural order from 0 to 7. 8 to 15. That's rule number 1. Then rule number 2 is whatever number you see on the top, you make a circle. 0, 0, 10, 3, 5, 6, and 14. Then what happened? All these circles stands the output equal to 1. For those who are not circled, that stands for 0. Okay? Then we are going to have a lovely result. What is that? All right. So we are going to have a residue map this way. It's not like this one. Okay? This is W, 0, and 1. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we check the summation of sum of midterms. We have 0, we have 1 over here, we have 10, we have 3, okay, we have 5, we have 6 and 14. Okay, now this is important. Okay, because this is residue. This is X, Y, Z. Okay, X, Y, Z. What's the residue over here? Okay, this output is totally opposite to the W. So we're going to have a W bar. This is circled, right? This is 1, but here is 0. And this is 0, this is 1. So the residue here is reverse of the W. So we are going to have residue over here, W bar. And this one, we have 0 map, a map with 0, 1 maps to 1. So what is the residue here is W. And this is W bar. Okay, both of them are not circled. Okay, now not circled. Definitely they will go to the ground. This is 0. Okay, and this is W. And this one is always high, don't care. So this one always goes to 1. And this one always goes to nothing. So this is a residue map. Okay, we are going to use this. Okay, this is WXY, right? WXY. So the basic idea to implement this equation, this circuit is that if you remember the multiplexer that we learned in your first year, so this one goes to the selection line. And this one goes to the, this one is the input lines. This is a very basic idea, okay? Use this as the selection line, this is the input lines. So what's gonna happen? We don't have to go to bother. We just use very large multiplexer. Okay, 1, 2, 3, X, Y, Z. They are going to select 0, 1, 2, 3, 4, 5, 6, 7. And this one, W bar. This one is W. And this one goes to W bar as well. Number 4 goes to the ground. This one goes to the ground as well. And this one goes to the W. And this one goes to 1. This is the easiest way to implement it. Is that right? So remember, I'm not sure whether you took my course when you were a freshman. Remember I said one thing in the digital system design. If you have a large enough multiplexer, you can implement any given Boolean equation. This is one of the ways. Use the residue map. Is that clear? Right? So how the hell we use that thing? Use this way. Okay, these are residues, and these are selection line. These are the variables that we decompose. Okay, but however, this textbook uses a different approach, and it's more efficient. Okay, the idea is the same. Basically, it's a multiplexer idea. All right, I'm sorry. Before we go to the circuit design, we can see different decomposed approach. See, this is a very big one. Okay, 5 variables, very big, and all students hate it. All right, we have summation of mean terms. Then these are don't cares. These are don't cares. Then we can decompose that like this one, 0, 0, 2, 1, 1 as well. And because we have 5 variables, right, we select 2. So we have 0, 0, 0, 1, 1, 1, and 1, 2. And then we plug in all the numbers in the natural order from 0 to 7, 15, 30, 23, 31. Okay, we have to reverse it because it follows the K-map way to do that. Anyway, and remember to circle all the numbers appearing, showing up in the mean of summation of mean terms, and the stars are don't care terms, 15, 17, 19, 23. Okay, and this is another way to do the resting map. It's more complicated. Now let's go to see the next slide. Okay, this is example I show you. See that? Almost the same, but different example. Now let's go back to an easier one. Okay, 4 variables from 0 to 15. See that? And these are the selection lines. And we have one, we have selected the last one as the residue. We circle all the mean terms. And then we derive, okay? They are all circles. It's always 1, 1. And this is nothing. This is Z bar. Z is nothing, and this is Z bar, and Z. And after you derive the residue map, then you can go to at least use the multiplexer to implement it. All right, let's take a break. I will be back after 5, maybe 10 minutes. Let me get a cup of coffee. I will be back.